logical. Umbilical, my universe is radical. Introduce the nation to embracing what is factual. Feminine energy, almost mathematical. You can't really sum up what is infinite and valuable.
A while back, some theoretical computer scientists and physicists had a really cool idea. What if we were to augment our good old deterministic computer algorithms with a new ability that's widely discussed by physicists and philosophers? The new ability I refer to here is, of course, randomness, random number generators. So informally, the ability to roll dice or toss coins. This new ability led to a brand new field that's flourished for many decades, probabilistic computing. So here's a snapshot of some pseudocode that solves the problem of determining whether a number n with, let's say, 10,000 binary digits is a prime. The actual details aren't that important. The one thing I want you to notice is that the very first line of code generates a random number, let's say by rolling a 2 to the power of 10,000 sided die. Now, in physical reality, you cannot build a 2 to the power of 10,000 sided die, but that's not a real problem because this is the same thing as flipping 10,000 fair coins. And flipping 10,000 coins is perfectly feasible in physical reality. Just, take your $100 bill to the bank, ask for pennies, and get flipping. Okay, now what are the benefits of using randomness to solve algorithmic problems? Well, one benefit is it gives you a great speedup for a particular classical number theoretic task, namely computing the primality or compositeness of an n-digit number. With a probabilistic computer, this can be done in roughly n squared steps. So if n is, let's say, 10,000, that's 100 million steps, and that's perfectly fine for an ordinary laptop. You can compare this with the fastest known primality testing algorithm that uses no randomness, which takes something like n to the 6 steps, which would be 10 to the power of 24 if n is 10,000, and that's completely infeasible. 10 to the 24 nanoseconds is like 30 million years. Probabilistic algorithms also give some mild speedups for some other compute function type tasks. But when it comes to, let's say, using probabilistic computing to speed up classical computer function type tasks, one might ask, is this it? Well, the answer is not at all. What's wonderful about probabilistic computing is that it can solve inherently probabilistic problems as well. Things like simulating a stochastic system or simulating a complex system that's too complicated to be simulated otherwise, generating probabilistic data. And it even motivates us to study new algorithms for statistical problems. Now, history began to repeat itself a few decades later when some theoretical computer scientists and physicists had a really cool idea. What if we were to augment our good old deterministic computer algorithms with a new ability, one discussed widely by physicists and philosophers? And this new ability I refer to now is quantum dice, or let's say the ability to manipulate particles at the quantum scale where new and different laws of probability hold. And adding this ability leads to the idea of quantum computing. Again, here's a snapshot of some pseudocode. Don't look at it too carefully. It's code originally designed by Peter Shor that solves the problem of factorizing a number n with, let's say, 100 binary digits. Again, the actual details aren't super important. The only thing I want you to notice is that the first few lines describe getting hold of, let's say, 10,000 trapped ions and physically manipulating them to produce what I'll call a quantum die, the quantum generalization of a probability source. Now, turning this code into physical reality is in principle possible, but it still remains an enormous practical challenge for these days. Here's an example picture of 2 trapped ions waiting to be manipulated. Okay, again, we can ask, what are the benefits of quantum computing for solving algorithmic problems? And the most famous one is the one I just mentioned, that you would get a super great speedup for a particular classical number theoretic task, namely computing the factorization of an n-digit number. With the quantum computer, this can again be done in roughly n squared steps. And you can compare this with the fastest algorithm we know on a quote-unquote classical computer, which would take exponential in n many steps. There are other quantum algorithms like Grover's algorithm that give you, let's say, mild speedups for other classical computer function type tasks. But again, some might say this is all that we have for using quantum computers to solve classical computer function type tasks. So is this it for the usefulness of quantum computers? Well, again, no, and for the same reason. So one realm of applications that I find very exciting is using quantum computers to solve inherently quantum tasks. Things like simulating molecules or other quantum systems, or for tackling quantum statistical problems. And this upcoming series of videos I'll present will describe some recent advances on such quantum stats problems, and in particular, the basic task of learning a quantum state. So here are just a few things we have to look forward to. I'll start out by describing what is a quantum die or a mixed quantum state. And we'll see how we can try to learn quantum probabilities from quantum measurements. We'll talk about symmetry and the role that group theory plays in quantum statistics. And finally, for the especially hardcore math enthusiasts, we'll end by discussing a new and unexplored kind of random matrix.